Ronald Fisher was the pipe-smoking statistician who mistakenly argued that, yes, although a lot of smokers develop lung cancer, perhaps there's another hidden cause that leads people to like smoking and to develop cancer. Can we ever be sure that smoking causes cancer? Consider another example. Ice cream sales correlate with homicides. Does this mean ice cream consumption causes murder? If we removed ice cream consumption, would this be accompanied by a drop in the murder rate? In principle, we could test this. We could set ice cream consumption to a certain level in various cities with the roll of a die. Any connection between ice cream consumption and some hidden factor would be removed. So, if ice cream doesn't cause murder, we'd expect to see no correlation between consumption and the murder rate in each city. However, if the correlation remained, this would be proof that ice cream consumption is a cause. The power of randomized trials is that they allow us to discover causal relationships from simple correlations, as long as we control the experimental setting. However, randomized trials aren't always easy or ethical to run. For example, it's unethical to conduct a trial in which people are forced to smoke a certain number of cigarettes to check whether they cause lung cancer. If we cannot perform a randomized trial, we must think about all the possible factors that may somehow affect a relationship. These intervening factors are called confounders, as they may confuse the relationship between the variables of interest. A causal network is a directed graph between a complete set of variables relevant for a particular process that describes the conditional dependent structure between the variables. This network is hypothetical and needs to be confirmed with data, but this seems very difficult. Consider the simplest closed system with just two variables and lots of data. If we see a relationship between A and B, then it could be because A causes B or B causes A, and nothing in the world would help us tell the difference. Are married individuals happier than unmarried ones because they are married, or are happy individuals more attractive marriage partners? We would never be able to tell. And if you're not able to tell in the simplest possible system, then how is it possible in larger systems? Actually, this is a case where larger is better. Fortunately, in the 1990s, Spirtes and Clark Glymour came to the rescue with their PC algorithm, which is based on simple but powerful ideas to allow data to determine causal relationships. Say we want to know the causal relationships between the number of COVID-19 cases, the adherence to mask-wearing rules, and the severity of social distancing measures. Initially, before collecting any data, experts believed that whereas social distancing was effective in stopping the spread of the virus, face masks were not. The idea was that consumer-grade face masks were unable to protect the wearer from the airborne virus, but that sufficient distance would. Say we collect data from European countries and observe that there seems to be no relationship between the mask-wearing adherence and the severity of the social distancing rules, but both are negatively correlated with the number of COVID-19 cases. The correlations that we observe create this graph, in which the relationship but not the causal directions are indicated. This means that there are four possible configurations of the causal graph. However, the first three causal graphs would all lead to an observed relationship between mask wearing and social distancing, which is not borne out by the data. For this reason, the causal graph has to be this one, since it's the only one that agrees with our observations. Remarkably, we've been able to learn about the causal relationships from observed correlations only. Sometimes, correlation does imply causation. In fact, epidemiologists, including Sir Richard Doll and Sir Austin Bradford Hill, showed conclusively in the 1950s through observational studies that smoking does cause lung cancer. The COST Action COSTNET consists of a collaboration of more than 500 researchers across 34 countries and is funded by the EU to carry out research into network data science. Our research is crucial to understanding and controlling infectious diseases, but also the stability of global financial networks, novel drug targets in genetic networks, underreporting in arms trade networks, as well as novel discovery methods for causal networks.